So we ended with catalysts and just talking about what their purpose is in a reaction. The first part of today, what we're going to do is we're going to talk about looking at like rates of reactions in terms of math, very simple math, and then we're going to go on to use data to write rate laws. So in a chemical reaction, you can focus on the rate of reaction three different ways. You can see how fast or slow a reaction is going depending on how fast or slow a reactant is consumed. Or you can focus on how fast a product is being made. Or you can kind of look at it overall. And again, reaction rates are going to be found by change in concentration over change in time. So that triangle means change. It's the delta triangle. Those brackets mean concentration. And this is going to be the generic way we describe a rate. So again, rate is, for this class, is the speed of a chemical reaction. So like in everyday life, the rate at which you drive is distance over time, right? And when we talk about us driving, we use that as miles, distance per hour. That's how we describe the rate at which we drive a car. Well, in a chemical reaction, we're not driving, right? So our chemicals are described generally in concentration, because that's the unit that that talks about how much of them you have, over change in time. Now, usually this is in molarity, molarity over second. So concentration, change in concentration over change in time. But sometimes the units for time will change. Sometimes it's molarity per minute, sometimes it's molarity per hour, but again, it's concentration over time. And this term right here, change in concentration over change in time, this entire term is called rate or speed. This whole thing means the rate or the speed. And if we have a reactant that we're discussing, we throw a negative out in front of it just because it's losing concentration over time, because reactants get used, so they go away, and they go away because new products are forming. So our products end up being a positive rate. Now, rates aren't ever really negative. They're just the negative means you're losing that concentration over time, and the positive means you're gaining concentration, because reactants get used up and products get made. So reactants should always decrease in concentration over time, and products should go up over time. That's the whole point of a reaction, to get rid of your reactants to make products. So we're going to do a practice run first, where we're going to calculate the average rate. Now remember, rate means change in concentration, and this problem is focusing on some substance A, over change in time. That's what this word means, is this whole term. And then I give you some data of a certain amount of time. So I say the concentration of reactant A at 20 seconds is 0.54 molar, and then it drops down to 0.3 molar at 40 seconds. So obviously reactant A is decreasing concentration over time. So we have a decrease in concentration of A over time because it's a reactant. At this point, we just plug in. So now I know we keep saying A means, or triangle means change, but mathematically it means final minus initial. And you should remember this back from the thermo chapter. Change means final minus initial. Final whatever minus initial whatever. So on the top, change in concentration. Final concentration is 0.30 molar. Minus initial concentration is 0.54 molar. Over change in time. Final time is 40 seconds. Initial time is 20 seconds. So this is molar. This is seconds. Now don't forget that this guy goes out in front because you're losing concentration over time because you're a reactant. So when you calculate it out, I wrote it in scientific notation, but you can write it in standard notation. So you're losing this much concentration per second of reactant A. This is standard notation. This is scientific notation. Well, you can throw a negative out in front of there, but just remember that this just means it's kind of like heat, that you're just losing concentration over time. There's no such thing as a negative rate. You can't go negative speed, if that makes sense. So the negative, again, kind of like the thermo chapter, is descriptive. You're losing concentration over time. So like when they say calculate the average rate at which A disappears, this word right here is really implying the negative concept. This is how quickly it's disappearing. Okay. So now when we're comparing the rate of a reaction and not just focusing on one substance, we will use stoichiometry. So you have a generic reaction A, B, C, and then the little numbers in front are our balanced coefficients. And then notice that we have these terms right here. These are all change in concentration over change in time, which means those terms mean rate or speed of the reaction. Now notice that the coefficients go in the denominator. So this is 1 over its respective coefficient, 1 over its respective coefficient, and so forth. Also pay attention to the fact that your reactants have negative signs in front of them because they lose concentration, whereas your products, I mean, they don't have a positive sign in front of them, but they are shown being positive because they gain in concentration in a chemical reaction. And so you can use stoichiometry from a balanced reaction to discuss the respective rates of one another. So things can lose concentration faster than things gain, and vice versa. So the rate of a reactant or a product, they don't have to be equal. Like you can lose one reactant faster than you're gaining the product. So we're going to do some practice with this, 2 practices actually, and then we will go from there. So we have this reaction where HI is decomposing into H2 and I2. And then before we do the math part, I just want to look at this conceptually. So now instead of like talking about these in terms of mole ratios, which we can, we're also going to talk about it, the stoichiometry, discussing rates. And what this means is that you will lose HI twice as fast as you gain H2. And you will lose HI twice as fast as you will gain I2. Now, what about H2 and I2? They're being produced in the same ratio. So they should be being produced at the same rate. That's all this concept is. Now, mathematically, based on the last slide that I show you that had 1 over the coefficient, 2 over the coefficient, whatever, let's write it based on this one. We're going to focus on H2, HI, and H2. Just we're going to look at the rate of HI compared to the rate of H2. Okay? So how do you do that? Well, we said that you go like this. What does rate mean? Rate means change in concentration over change in time. And we're comparing that to H2, right? So the change in concentration now we have to pay attention that HI is going to lose concentration while H2 is going to gain concentration because H2 is a reactant, or HI is a reactant and H2 is a product. And then based on that last slide, how do you account for the coefficients? Well, you do 1 over their respective coefficient. And for this one, you would do 1 over, there's a 1 in front of here, right? So how would you compare the rate of HI to the rate of H2? Well, you would just rearrange. Solve for the rate of HI. Now, leave the negative sign over here because this guy's going to lose concentration. How do I get rid of the 1/2? Well, that means I'd multiply by 2 over 1. Is that right? That's the reciprocal. So this is gone. So this ends up being 2. Okay, so how do you read this? You lose HI twice as fast as the rate of H2 is being produced, which we just said verbally looking at this. This guy gets depleted twice the rate that H2 gets produced. So if the rate at which H2 was produced was 4, the rate at which HI was losing would be 8. Double. It would be 8. The rate of HI would be 8 and the rate of H2 would be 4. That's all this is saying. And now this would be the same for if we did HI to I2, only because the ratio between HI and I2 is identical as the one we just did. So you lose HI twice as fast as you make either of the products. And again, this is based on stoichiometry right now. So let's do one more. First thing, I give you ozone decomposing into oxygen. I need you to balance it. I didn't balance it for you. Not a very crazy balance, right? There should be a 2 here and a 3 here. So just conceptually, before we do the math, are you losing ozone quicker than you're making oxygen, or are you making oxygen quicker than you're losing ozone, just based on the stoichiometry? You should be making oxygen faster than you're losing the ozone because it's a 2 to 3 ratio, okay? So what they do is they say, how is the rate at which ozone disappears related to the rate at which oxygen appears? Well, remember, rate means change in concentration over change in time. So how would we write that for this specific reaction? Well, ozone is going to lose concentration because it's a reactant, and the rate would be change in ozone I should put that over change in time. And then you set that equal to. Now the rate of oxygen would be the same term, but you're going to have oxygen in there, right? Because this term means rate. So we're going to have change in oxygen over change in time. Now this should be positive, right? Because oxygen is being produced. So we should be making oxygen. And then of course we have to consider their coefficients. So this is 1 over 2, because there's a 2 out in front of it. And this is 1 over 3. because this is out in front of it. And so this is the expression for what they asked you. This is the rate at which ozone is used compared to the rate at which oxygen is produced. So the second part gives you the rate at which oxygen is produced. So they do this experiment, they go, oh, I know how quickly oxygen is appearing. I have a number for it. So the rate at which oxygen appears. So literally, this is the rate of oxygen. Remember, this term means rate or speed. And they tell you it. So like you have this whole term. It's this number. They want to know, okay, if you know how quickly oxygen is appearing, let's work backwards and figure out how quickly ozone is disappearing. And we're going to do that based on stoichiometry. So all you have to do is get the rate of ozone by itself. Now remember, this term is the rate of ozone. So all we got to do is move this fraction over, right? How do we move a 1/2 over? Well, you do it by multiplying by the reciprocal, which is 2 over 1, right? 2 over 1. So now this cancels. And you end up with 2/3. And then you plug this number in. 2/3 times 6.0 times 10 to the -5th. Because they gave you that in the problem right here. Now, don't use calculator yet. This is something they could give you without a calculator. So how do you do it? Very, very, very simply. Multiply the top part out first. The fraction just gets multiplied by this coefficient out front, this 6, right? 6 times 2 is 12. 12 divided by 3 is 4. 4 times 10 to the -5th molarity per second. So this is the rate at which ozone is disappearing, which is what this negative implies. We're losing it, compared to the rate at which oxygen is appearing. So you will see, based on that ratio, oxygen is appearing a little bit faster than ozone is disappearing. Not a lot, but a little bit. Okay, so that's it for this part. Now we're going to write rate laws again. And we're going to write rate laws based on data tables now. So before we were doing this, we were writing rate laws based on mechanisms. We found the slow step and we wrote the rate law based on the slow step. Now remember, when you go to write rate laws, it's always rate equals K, and then we focus on the concentrations of our reactants and we raise them to a certain power. Okay? Those powers, those M and N, are called orders. And for this class, they're only going to be one of 4 numbers, 0, 1, 2, or 3. 0, 1, 2, 3. They're not going to be anything else. Now, they can be other things, but for this class, they won't be. The only thing that changes the rate law constant is temperature. So assuming we're talking about the same experiment, you can mess with everything in terms of concentrations, but the constant won't change unless you change temperature. And we'll talk about why later. The only other time a rate law constant will change is if you're doing like a totally different experiment. Okay. And the way that they find these M's and these N's, these orders, are by actually performing the experiment. And that's what we're going to show you today. Them doing a bunch of different experiments to determine the rate law for the reaction by finding the orders. So kind of bear with me as we go through this. If a reaction is 0 order, with respect to a reactant, it means that reactant has 0 effect on the speed or the rate of the reaction. And you go, well, why is that? Well, if we go to write a rate law that's 0 order, we do this. How do you write a rate law? You write rate equals K, and we're using fake reactant A. And if it's zero order, we write the zero as an exponent. Well, anything to the 0 power is 1. So this guy is like just gone, meaning you don't even see it in the rate law. So it doesn't affect the rate of the reaction. So if I change its concentration, it doesn't matter. I can increase its concentration, lower its concentration. If something is 0 order, it means that no matter what you do to it, it doesn't change the speed of the reaction. Now be careful. Just because you don't include it in the rate law does not mean it is not part of the chemical reaction. It is still present for the chemical reaction. It just doesn't affect how fast the reaction goes. It's part of the reaction, but won't determine the speed of the reaction. Okay? So now we're going to go through the next one. So there's 0 order. Now there's first order. So first order, how would I write a rate law? I would write rate equals K, some substance A, and first order means there's this like 1 up here. Your order is your exponent. So how does this work? Well, what happens if you notice rate and concentration are a direct proportion? What does that mean? If concentration goes up, so should the rate in general, the speed of the reaction. If concentration goes down, so should the rate. So what happens now? We have some substance A, all right? It has a set concentration. And then I go in and I double it. What happens if you double it? Well, 2 to the 1 is 2. So whatever this rate was initially, it's going to double. So what happens if I triple the concentration and it's first order? Well, if it's first order, this is a 1, right? 3 to the 1 is 3. So the rate would also triple. What if I quadruple it? The rate would quadruple. What if I change it by a factor of 10? The rate would change by a factor of 10. Meaning if something is first order, whatever you do to the concentration, the same thing happens to the rate. If I decrease the concentration in half, the rate will decrease in half because it's first order. That is how first order reactants affect the rate. Whatever that happens to the concentration, the same thing happens to the rate if it is first order. Okay. It gets harder when it's second order because now my exponent is a 2. So if you go to write a rate law that's second order, if it's second order, your exponent is a 2. Well, uh-oh. So I have some rate with a concentration, and then let's say I double the concentration of that substance in a different experiment. Well, if it's second order, what happens? What's 2 squared? 4. So the rate would change by a factor of 4. What happens if I triple the concentration and it's second order? Triple the concentration. The rate would change by a factor of 9. So in first order, so in 0 order, you change the concentration and nothing happens. In first order, whatever you do to the concentration, the same thing happens to the rate. In second order, it doesn't follow a set rules. You just have to square whatever you're doing to that concentration. So if it's second order and you double the concentration, the rate doesn't double, the rate actually quadruples. If it's second order and you triple the concentration, the rate doesn't triple, the rate actually changes by a factor of 9. And then finally, even wilder, I guess, is third order. So if you write a rate law that's third order, you would write rate equals K, concentration of A to the third power, because it's third order. So a third order reactant doubling its concentration, if it's third order, 2 to the third is 8, so the rate would change by a factor of 8. A third order reactant, if a reactant is third order and you triple its concentration, your rate's going to change by a factor of 27. So these are the only orders that we will do: 0, 1, 2, and 3. okay? So this is the summary of everything I just said. And again, this is our generic rate law. Rate equals K, some reactant A raised to some order, some reactant B raised to some order. And then I briefly mentioned this in the past, but the overall order is the sum of your exponents. So let's say a reaction is second order and first order. The overall order is 3 because 2 plus 1 is 3. Let's say the reactant is 0 order and first order. The overall reaction is first order because 0 plus 1 is 1. Let's say it was second order and second order. The overall order is 4 because 2 plus 2 is 4. Any questions on how to figure out the overall order? You can't figure out the overall order unless you know the order of each reactant. All right. So here we go. They call this the method of initial rates. And what you will notice, the difference between writing a rate law the way we had done it and this is what's given. The last way we learned to write a rate law was based on a mechanism. So you had like step 1, step 2, step 3, and then they said the slow step, and then you wrote the rate law based on the slow step. And in fact, it was pretty easy to do. Unless the first step was fast, then it took a little bit more work, but not as much as this is about to take you. Okay? I need you to bear with me while we do the long way a few times, and then I will show you a shortcut way. I do want to emphasize, once I show you the shortcut way, it is still required that you show work. And I'll show you the work that's required. It just won't be as much work as we're about to do right now. So what I mean is on the AP test, when you write a rate law, you can't just write a rate law and not show them how you got it, even if you got it right. So I'm going to show you the long way to get the rate law, and then I'll show you the shortcut way. Both require work, so you will always have to show work. Once I show you the shortcut way, it will probably be very easy for you to write rate laws without showing work. You can't do that. You have to show how you got it, okay? So having said that, I'm going to do a flashback. This has nothing to do, what I'm about to ask you has nothing to do with this chapter. And has everything to do with prior knowledge. And so far, I don't think anyone's gotten it in all my classes. What type of reaction is this? It is redox. So now the question becomes is, you should know that. So let's flash back on how we know. Well, there's a couple ways to know. The more work way to know is this. Look it, you instantly can see bromide is -1 and it's 0 here. I had a change in oxidation state, boom, it's redox. If anything changes oxidation state, it's redox. But there's actually an easier way to notice this that I told you about a while back ago when we did the reactions in an aqueous solution chapter. Does anybody remember a hint that a reaction might be redox based on the way they present it to you? This should look like a net ionic to you. And the question is why does it look like a net ionic? Well, because you see charges, right? That's a big hint that it's a net ionic. I see charges in my overall reaction. So, having said that, I want to kind of point out, again, this has nothing to do with this chapter, but still is related to chemistry. I want to point out that bromate just doesn't exist. BrO3 is bromate. If I were to go to the back and I wanted to do this reaction and I had to yank chemicals off of the cabinet, out of the cabinets to do this reaction, I couldn't just go find bromate. I could have a salt that has bromate in it, like sodium bromate, potassium bromate, lithium bromate, something bromate, but there's no such thing as just bromate. So maybe I yank sodium bromate off the shelf. Sweet, now I have a source of bromate ions, right, that are participating in the reaction. Well, what about bromide? Same thing. There's no such thing as just bromide sitting on my shelf back there. There's sodium bromide, potassium bromide, lithium bromide, all sorts of salt bromides. So let's say I take sodium bromide. So I've taken sodium bromate, sodium bromide. What's H plus? It is hydrogen ion, but like, what is it? H plus is telling you that it's a what? Acid. So having said that, do you think I just have H plus sitting back there? I don't. What if I pulled like hydrochloric acid off the shelf? Sure. Does that have H plus ions in it? Yes. What if I pulled nitric acid, HNO3? Does that have hydrogen ions? Yes. So what I'm trying to tell you is that when you see a reaction like this is net ionic, one, it's most likely a redox, and two, these aren't the full chemicals. This has gotten rid of who? Spectator ions, right? If I take sodium bromate, do you see sodium in this reaction? No. Where is it? I canceled it out. Why? Because it doesn't participate in the chemical reaction. It's a spectator ion. It's just like sitting there minding its own business. Okay? I'm just kind of revisiting this redox concept because you're going to revisit it again this semester. We're doing redox again this semester. Okay? All right. Now done with my little tangent. So if you look at this chart, this is a data table. So we're going to write a rate law based on a data table now instead of a mechanism. So I have all these different mixtures, also known as different trials. So they did like trial A with a set number of concentrations, and then they did a separate experiment with mixture B, and then they did a separate experiment with mixture C, and so forth. So they do the experiment, they set their numbers, and then they do it. They start over and do it again with different numbers, and they start over again and do it with different numbers. Okay. I'm going to teach you the easiest way to do this today. I will show you, well, not the easiest way. I'm going to show you the easiest method to do it that doesn't always work, but for today it will work, and then we will get to one where it doesn't work on Friday. So if we're looking at concentration, right, so we're trying to find the rate of a reaction, and we're going to mess with concentration because we know messing with concentration can change the speed of a reaction a lot of the times. So if you want to find, your whole job is to find the rate law. So what does that mean? I want the rate law of this reaction. So what does my rate law look like? It looks like rate equals K, concentration of bromate. I wish that wasn't so, I'm going to redo this because I want it to be nice. So rate equals K, concentration of bromate raised to some power. Bromide is another reactant raised to some power. And hydrogen ion raised to some power. I don't want to use O, like MNO, because O looks like a 0, and we know 0 can be a power, and I just don't want to confuse it. So you used to be able to do this given a mechanism. They said the slow step, and you literally just wrote the rate law based on the slow step. Easy peasy. This is much more complicated. Basically, your whole job right now is to find these powers or these orders. And it's based on what's known as the method of initial rates. So here's the strategy. You'll probably want to write this down. If you want to figure out, this is the strategy that works most of the time. Not all the time, but most of the time. If you want to find out what the order is, this exponent, with respect to bromate, the easiest way to do this is to make sure that the other two reactants aren't changing. Okay? So here's the first example I'll do for you. I'm going to compare experiment A to experiment B. They're two separate experiments because I see that bromate changes concentration. So in experiment A, they used one concentration, and then experiment B, they did a different concentration of it. And I noticed that between experiment A and B for the bromide and A and B for the hydrogen, that those guys didn't change. So what does this do for us? Well, if bromate is changing in concentration, but the other two guys aren't, if the rate changes, it's probably because of bromate, because the other guys didn't do anything between the two experiments. So if you hold them constant, while only one thing changes, you can focus on just how that one thing is changing the rate. That's the strategy to do this. Hold on, I see a couple questions, but I might have just missed this. Yes. Okay. So here's what you do. You set them up in a ratio. Here's what I mean. Again, we're focusing on experiments or mixtures A and B. So you write rate laws for both of them and you divide them. You set them up as a ratio. Now, how do you pick who goes on the top and who goes on the bottom? Technically, it doesn't matter. However, I generally like to put the bigger numbers on the top and the smaller numbers on the bottom so I don't end up with fractions. I don't like fractions, but it doesn't have to be that way. So I'm going to do the first way as a fraction and it will be fine. So I'm just going to do the rate law for A and I'm going to compare it and or divide it by the rate law of mixture B. So how do you write rate laws? Rate equals K, right? Now, if this is for A, I'm going to use all of the data for A. So my bromate is 0.0050. I don't know its order. My bromide is 0.025. I don't know its order. My hydrogen is 0.030 and I don't know its order. This is the rate law for A being compared to the rate law for B. Well, rate equals K. Now for B, I'm going to use all of the data for B. Notice that these are only reactants, right? Because rate laws have reactants in them. So this is bromate again. This is bromide again. This is hydrogen ion again. So this is the point right here. Look at the hydrogen ion on the top and the bottom. It's the same. So mathematically, if you have the same number on the top as you do on the bottom, what does it do? It cancels, right? What about the bromide, Br minus? Same number on the top as on the bottom. We strategically did this on purpose, right? We forced them to cancel. So now what we're doing is we're looking only at how bromate changes the rate of the reaction. Now, I forgot to include one thing. I haven't plugged in the rate yet. I have a number for rate. That's this column right here, initial rate. So A is 10. B is 20. So 10 divided by 20 is 1/2, right? Equals, your K's cancel. 0.005 divided by 0.01 is also 1/2. Raised to the m power. Some order. 1/2 to the what is 1/2? 1. So you have just found the order, first order, with respect to bromate. That is the substance we were focusing on in this part. So now if you go back to your rate law, you know bromate right here. I'll just do this real quick. Bromate is a 1. Now you're going to learn that we don't write ones for first order. Just writing the substance itself implies a 1, but for now, let's just do it. We just found out bromate is first order. Okay, so we go next. Let's do bromide. So if we want to focus on the order of bromide, we would like the bromate and the hydrogen ion to not be changing. That is ideal. It is possible to do it when that doesn't happen, but for right now, that is the most ideal if we can make it work. Which two experiments will that work for to compare? Or which two mixtures? B and C. Very good. B and C. Bromide is changing between B and C, while these guys are remaining constant. So now we can just focus on how bromide is affecting the speed of the reaction. Because if the other guys aren't changing, they're not changing the rate of the reaction because you leave them the same. They're remaining constant. So how do we do this? So we do the rate of one of them compared to the rate of another one. Now, I don't want to do fractions, so I'm going to go back to my initial strategy where you pick the bigger number to go on top. So look at this number is bigger, so I'm going to put C on top. Or you could have looked over at the rate. This number is bigger, so I'm going to put C on top. So C on top, B on the bottom. And you write rate laws for both of them. Rate equals K. Rate equals K. And then you plug the respective numbers in. So if I'm doing C, all of C's numbers go on the top. Whoa. And then I'll just do a different color. All of these numbers go on the bottom. So this is 0.010 raised to some order. Now we actually already know that's 1, right? You could plug that in because we do know it's 1, but I'm just going to ignore it for right now. And then all of B's numbers go down here. Now bromide changed. Okay, so again, look at same exact number, they cancel out. Same exact number, they cancel out. My K's cancel out. Now, I haven't plugged my rates in yet, so I do need to do that. That's this last column right here. The rate for C is 40, right here. And divided by the rate for B is 20. 40 divided by 20 is 2 equals 0.05 divided by 0.25. It's like the same as saying 50 divided by 25, right? It's 2 to the n. Because, right, this is what we're trying to find. 0.05 divided by 0.025 is 2. So what's this order? 2 to the what is 2? 1. So it's first order. With respect to bromide, Br minus. So now if I go back to my rate law, I now know this guy's order. It's a 1. One more. So hydrogen ion. Hydrogen ion. Let's see. So if I want to find out the order with respect to hydrogen ion, I would like the hydrogen ion to change concentration, but the other two things to not change. Which reactants or which reaction you want to pick, or which two mixtures? There's actually really only one option. Bromide stays the same between C and D, so does bromate. whereas hydrogen is changing. Again, who goes on the top? Well, this number is bigger than this number, so I'm going to put D on the top. You also could have said this number is bigger than this number, so D on the top. So rate of D compared to the rate of C. And so what we do is we write rate laws for both of those. Rate law for D is rate equals K. Now I plug all of the information in from D. That all goes on the top. And then I do it again for C. So I plug all of this info in for C. Rate equals K, some order, okay? And then let's plug my rates in. So my rate for D is 160. And my rate for C is 40. 160 divided by 40 is 4. Equals. My K's cancel. These are the same exact number. These are the same exact number. So all I'm comparing are these two. 6 divided by 3 is 2. And then we're trying to find the order, right? So 2 to the what is 4. 2 squared is 4, right? So it's second order with respect to H plus. So if I go back to my original reaction, or my original rate law where I hadn't had the orders yet, we know that bromate is first order. We know that bromide was first order, and now we know that hydrogen is second order. In other words, when the concentration doubled for hydrogen, the rate quadrupled. That's what it means to be second order. So this is my rate law. Rate equals K, the concentration of bromate, the concentration of bromide, and the concentration of hydrogen raised to the second power. Now, I'm going to get rid of these. You don't really see ones written in rate laws. Writing the substance itself implies that there's one of them. It is simple. It is a little bit tedious, right? Which is why I'll show you a shortcut in a little bit. Especially when there's 3 reactants. The one we're going to do next only has 2 reactants, so it will be a little bit less tedious, but you're right, it can be kind of tedious. So now, if I can, what is happening? So now, if I were to ask you the overall, this part right here is just explaining everything we just did in words as opposed to in math, okay? What is the overall order for that reaction? It's first order and first order, right? And then second order. So the overall order for that reaction would be 4 because 1 plus 2 is 4. So overall order is 4. Now we are going to do units. Ooh, units are a little bit painful. So I'm going to rewrite the rate law just real quick, and we're going to plug units in. What are the units for, so you want to just find the rate law constants units. The units for a rate is molarity over seconds most of the time. Concentration over time. And then we have K. What are the units for concentration? Molarity. What are the units for concentration? Molarity. What are the units for concentration? Molarity. But don't forget your H plus. There's a 2 up here. So this matters. So I got to get K by itself. So I divide everything by these guys. So now K equals, we can get rid of one of our M's, right? One on the top, one on the bottom. Now, you've got to distribute that 2 to the molarity. There's going to soon be numbers in here, which we'll work with later. But like if you do 2x squared, you don't just square the 2, you also square the x. You don't get 4x, you get 4x squared. So the same goes for the molarity. So this right here is molarity squared. So you have a molarity squared times a molarity in the bottom. So that's a molarity cubed in the bottom. So it's 1 over seconds and 3 molarities. However, 1, 2, 3. They don't usually write it like this. It's usually like this, where that negative sign tells you that that unit is in a denominator. So there's 3 molarities in the denominator. That's what the negative is for. And there's a second in the denominator. Why is the second in the denominator? Because this is molarity over seconds. Molarity per second. So both of those have to be in the denominator. And again, the K constants units are not always the same because the order is not always the same. So if this was second order, you wouldn't have as many molarities overall. If it was second order overall, so the K constants units will change, which is why they always ask about the K units on the test. And we'll do a bunch of practice with finding the K units. So you can't memorize the units for K is what I'm saying, because it changes based on the rate law. All right, last one today. So we're only going to be able to figure out the order of the reaction and the rate law. We'll have to start up with the rate constant and the units next class. So we're going to do the long, tedious way, and then when we're finished, I'm going to show you the short way. So we have a reaction. I give you an experiment. Very apparent there's only 2 reactants this time, which is less work then. So right, we have this generic rate law. Rate equals K. These aren't even real reactants, just so I don't know the order of that guy, and I don't know the order of this guy, and it's my job to find it. So let's do it. We're going to compare 2 of them. So let's see. For X, I see between experiment 1 and experiment 2, X is changing while Y is not. This is good to find X, because if X is changing and Y is not, if the rate changes, it's because of X. So I'm going to compare them. Who do I want to put on the top? Well, this number is bigger than this number, or this number is bigger than this number, so I'm going to put 2 on the top. This is only because I want to avoid fractions. You don't have to do it this way, but you'll likely end up with fractions if you do it the other way. So the rate of experiment 2 compared to the rate of experiment 1, and we write rate laws for both of them. So in experiment 2, X is 0.01 raised to some power, and Y is 0.250. Wow. Raised to some power. Oh, rate equals K. Sorry, I forgot the constant. Rate equals K. And then experiment 1, X is a different number to some order. and y is the same number raised to some order. And I go, oh, this worked out nicely for my, oops, I forgot a 0 right here. Okay, and I did this on purpose, right, so that this guy would cancel out to make my life easier. I haven't plugged my rates in yet. My rate for experiment 2 is 4, divided by my rate for experiment 1 is 1. So 4 over 1 is 4. My k's cancel. 0.01 divided by 0.05 is 2, or 0.005 is 2. Okay, so 2 to the what is 2, or is 4. 2 to what power is 4? So this is going to be a 2, which is second order. With respect to, wow, what is wrong with my pen? Oh my goodness. With respect to x. So I just found my order with respect to x. So this guy's a 2. Now I need to do it again, but for y. So again, we would like y to change and x to not change. Which experiments are those? Be very careful in this one. 1 and 3. So kids get used to doing like ones that are right next to each other, like 1 and 2, 2 and 3. It doesn't have to be that way. So we have to compare experiments 1 and 3. Why? Because this is where x is not changing and y definitely is. Now, who do you want on the top and who do you want on the bottom? Well, this number is bigger than this number. This is the one that's changing. So I'm going to have 1 on the top and 3 on the bottom. I actually couldn't use the rates to tell because the rate didn't change, which, really quickly, if you change concentration and the rate doesn't change, what order is that? 0, but I'm going to prove it. So rate of 1 compared to the rate of 3. So the rate from experiment 1 is the number 1. And the rate from experiment 3 is the number 1. So 1 divided by 1 is 1 equals, this cancels. Sorry, I keep forgetting my k's. That's my fault. But they cancel for right now, right? Rate equals 0.025 divided by 0.125. Like, just pretend these zeros are not here. 250 divided by 125 is 2. 2 to the what is 1? Well, 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. So the only thing this can be is 0 order with, oh my goodness, with respect to y. Meaning changing the concentration of y does not change the rate. The rate stays the same. That's what it means to be 0 order. So if you go back to your rate law, this is a 0. And in fact, because it is 0 order, you generally do not include it in the rate law because anything to the 0 power is 1. So this is a better way to simplify the rate law, is to omit the 0 order reactant. Now, I have 3 minutes. I need you to bear with me, please. I want to show you the short. So everything I just did is right here. Everything we just did is right here. If you want to go back and look at the work. I want to show you the shortcut way. So the shortcut way requires you to hold one of the reactants constant, or you can't do it. Well, you can later, but not yet. So here's what you do. We're going to look at X, right? We want to write a rate law. And we're going to focus on reactant X first. So you go, okay, what does a rate law look like? It looks like this. Rate equals K concentration raised to some power. Yeah? And we're going to focus on X. So for X, we said we kept 1 and 2. You use the same experiments, 1 and 2 constant, right? Because Y is not changing. What is the concentration doing for X between 1 and 2? So this requires you to be able to see the numbers conceptually. 0.005 to 0.01, the concentration is doubling, right? Concentration, that's what this bracket means, is doubling, right? What's the rate doing between 1 and 2? Quadrupling, is that right? 2 to the what is 4? 2. Yeah? So this has to be a 2. This is a lot less work, yes? However, you have to show this, at least this, by bare minimum on the test. I know you can probably see it conceptually, not even have to show the work. To get credit, you have to show the work. So the rate law is second order with respect to X. So now let's do it again for Y. We used experiments 1 and 3, right? Because X wasn't changing, so we could focus on Y. So I'm going to go from 3 to 1 when I'm looking at it visually, okay? So what is, right, we're going to look at Y. So the rate of Y comparing what's happening with Y equals K, some Y, we don't know the exponent. Hold on. So the concentration, which is this guy right here, if you look from 3 to 1, 0.0125 to 0.025 is doubling. Is that right? Doubling. What is the rate doing? Not changing. That would be 1 if it doesn't change. So rate equals 2 to the what is 1. That's a 0. Much less work. Both get the same outcome, but you must show the work even if you do the shortcut way. All right, thank you guys. I will see you on